Sorry, I couldn't hear you clearly. Could you repeat that again, please?
So, did you ask how the course was going?
Yeah.
Oh, it's going fine. Like, I'm not having any trouble so far.
How about the homework assignment?
So
Is it
Monday to Friday.
sorry? Your voice is not clear. I don't know if it's just me or can the others also not hear you clearly?
Can I just reconnect because my Wi-Fi is being.
No, no, no. It's better now. I can hear
Okay.
you.
No, are you talking about the one that's due on Friday?
Ah,
Oh, I think it's fine. Like, I just started working on it.
I had a question about the assignment.
yeah.
So in the first one, so like you given us a graph and you said we have to plot the data points, right?
Hmm.
So what exactly are we supposed to do? I mean, it's already in a graph.
No, no. So basically, what I want you to do is using some software, just plot them because afterwards I'm saying I also want you to find some function which might fit that.
Uh-huh.
So then you will also want to plot the function on top of that to check that that function is actually kind of close to those points.
Okay. Okay. And so while we're submitting, do we like take a screenshot and submit it?
Yeah, you can take a screenshot and so I'm guessing you will write your answers on paper and then you will take a picture of it, right?
Yeah.
So along with that, also put a picture of the graph and send that together.
Okay. Thank you.
So you all have the option of submitting the assignment on Canvas if you want, but if you prefer, you can also send it to me by email, whatever is convenient for you. Okay, why don't we start? Okay, so what did we do in the last lecture? This was essentially the calculus lecture in which, one second, in which we discussed differentiation and in particular we looked at one application of differentiation which was to find the maxima and minima of a function. Then we looked at integration and we saw that you can look at integration in three ways. You can think of it as taking a sum. So it's a generalization of the idea of taking a sum over a large number of small pieces. But you can also think of it as finding the area under the curve. And of course, you can think of it as being the opposite operation of taking derivatives or differentiating. And then in the end, we looked at differential equations, which are dynamical equations, equations which represent a change of one quantity with respect to another. Or if you want to think about it mathematically, it is just an equation which has a derivative inside it. And we looked at some applications of differential equations, like for example, predator-prey equations or modeling the growth of population. So this is what we did last time. Then after this, we also looked at kinematics. Kinematical equations, which involve velocity, which is the rate of change of displacement, and acceleration, which is the rate of change of velocity. And then we wrote down some kinematical equations based on these. by solving these differential equations. And then as homework reading, I suggested to you that you should read up about projectile motion. Does anyone have any questions about either the material that we covered in class or about projectile motion? Okay. You can also ask me tomorrow during the office hours if you have some pressing questions. All right. So having done this, we are now ready to start our second module. So we're starting physics properly. And this module is going to be all about mechanics. So this is Newton's laws and its applications. And as I had promised you before, as far as possible, whenever the situation arises, I'll try to give you some biologically motivated examples. So in today's lecture, maybe there won't be so much of that because today we're going to be covering mostly the physics basics. But in the next lecture on Wednesday, I think I'll be able to give you more biological examples. Okay, so let's start with a reminder of what Newton's laws are. There are three laws of motion that Newton gave. The first law was that every body continues in its state of uniform motion. And what is meant by uniform motion? Uniform motion means the velocity is not changing. So constant velocity until there is some external unbalanced force. So if there's something which is moving with some constant velocity, it will continue to do that. Nothing will change about it unless some external unbalanced force is acting on it. And of course, when I say constant velocity, I also mean an object which is stationary, because if it is stationary, then it has a constant velocity of 0. So if an object is just lying still and there is no force acting on it, it will continue to lie still. And if it is moving with constant velocity, then it will continue to move with constant velocity unless something is done to it. In some sense, if you think about it, it is almost obvious that if nothing is happening, if you don't disturb some system, then it's just going to continue what it is doing. Why should anything change about it? The second law of Newton tells you what happens now once the external unbalanced force acts on it. So Newton says that if you define a momentum, which is mass times velocity, then the force, and this is denoted by P, then this external unbalanced force, which is acting on the body, is going to be the rate of change of the momentum. So you can think of it as, because P is m times v and mass of the body is not changing, then you can relate it to the rate of change of velocity. But rate of change of velocity is just acceleration. So this is ma. So force is mass times acceleration. First law says that if there's no force, then the velocity is same. Second law says that once you apply a force, the velocity is going to change. So there is going to be some acceleration, and this force and acceleration are proportional to each other. F is equal to ma. And the third law says that for every action, there is going to be an equal and opposite reaction. So these are Newton's 3 laws of motion. Let's take an example and see what exactly they mean. So we'll consider a table and let's say there's a ball sitting on the table. And let's see what are the forces acting on it. So I'll consider the center of the ball, or what we call the center of mass. Later on, we will formally define what we mean when we say center of mass. Right now, just think of it intuitively as being literally the center of the entire mass. So what are the forces acting on this? There is the force of gravity, which is always acting, and that is acting in the downward direction. So that is given by mg, mass of the ball times acceleration due to gravity. Now, the ball is pushing down on the table. And therefore, by Newton's third law, the table must also push up on the ball. And that pushing up of the table on the ball is what we call the normal reaction force. So first, there is the downward gravity. Then there is an upward normal reaction, and this is normally denoted by N. Why is it called a reaction? Because this is coming from Newton's third law. Which says that if the ball pushes on the table, then the table also pushes the ball. And why is it called normal? Normal in physics usually means perpendicular. So when there are two objects touching each other, the normal reaction force is always going to be perpendicular to their contact. So over here, because the contact is on the surface of the table, this normal reaction is going to be perpendicular to the table. So we've taken care of Newton's third law, which says that for every action, there is an equal and opposite reaction. Now let's check what Newton's first law says. From Newton's first law, as long as there is no external unbalanced force, this ball will remain stationary. What this means is that the total force, since we know that the ball is stationary, we know that the total force must be zero. Or in other words, N minus mg is zero, or N equals mg. Why did I say minus mg? Because mg is acting downwards. So we always take that downwards to be negative, upwards to be positive. So the total force is N in the upward direction, mg in the downward direction. So total force is N minus mg, and that has to be zero. At any point, if you have any question, just type in the chat or just speak out, that's fine. So this is coming from Newton's first law. We say that two forces are balanced. That's why the ball is stationary. There is no net force acting on it. See, remember the wording of Newton's first law. There has to be no external and unbalanced force. Right now, there are forces. There is gravity and there is normal reaction, but they balance each other out. They are not unbalanced. That's why the ball is stationary. Newton's law also says external. So for example, the ball is finally made up of atoms, molecules, and these contain electrons, protons, neutrons. So there are some electromagnetic forces between them. There is electrostatics between the positively charged proton, negatively charged electron, etc. So there are internal forces, but that is not what we are concerned with right now. We are concerned with external forces which affect the total ball. So there is no external unbalanced force. That's why this fellow is at rest. Now, what if the table suddenly vanishes? Then we will have to start. Give me a good color. Okay, white. So if the table suddenly vanishes, now there is no reaction force because there's nothing pushing up against the ball. Now there's only one force downwards and it is unbalanced. So now we can start applying Newton's second law. Newton's second law says that F equals ma, but F, now the force, the external unbalanced force acting on it is gravity. So mg equals ma or g equals a. So what Newton's second law tells you is that the acceleration experienced by this ball, so this ball is going to start moving, it's going to fall downwards, and its acceleration is going to be given by mg, is going to be given by g. And then of course you can solve it. So you can say acceleration is just dv by dt. This is a differential equation. You know how to solve this. Last time we solved exactly this kind of differential equation, and then you will get something like v is v0 plus gt. Or if you want, you can further go and find out the distance as well, and then you will get something like so by solving this differential equation, now you can find out what is the position and what is the velocity of this ball as it is falling. So this is a simple application of Newton's 3 laws of motion. Any questions so far? This is the last time you're going to be learning Newton's laws formally in your life. So if you have questions, now is the time to ask. Okay. So what are some of the common forces that we are going to be dealing with? There's of course gravity. There is the normal reaction. These we have already seen. Suppose you have two objects that are tied up by a string, for example. Then there's a force in the string which is holding the things together. So this is called the tension in the string. And in a biological system, can you think of any case where there is something like a string which is holding two heavy things together?
Your muscles?
Exactly. So things like muscles, tendons, ligaments, these kind of things hold two bones together, for example. So later, maybe in the next lecture, we will see an example of Newton's laws when we are trying to look at tension in a muscle and how it helps you to lift weights. There are of course mechanical forces, which is just pushing, pulling kind of forces. There is electrostatic force, which if time permits, maybe towards the end of this course, we will talk a little bit about electrostatics. So these are some of the common forces that we see. Friction. This is one more force. So we'll try and look at some examples with these various forces. So as a first example, well, second example, since we already saw the one with the ball on the table, we'll consider a block which is sliding down a ramp. So there is an inclined ramp. Let's say it makes an angle theta with the horizontal, and we'll say there is some heavy block on this. This block has mass m, and this block is going to be sliding down. I want to find out what is the acceleration with which this block slides down. So once again, whenever you have this kind of problem, the first thing that you have to do is you have to list out all the forces that are acting on this block. So the first one is obviously gravity, and gravity always points downwards. So there is mg pointing down. The next thing is normal reaction. Because the block is on the inclined ramp, it's pushing down on the ramp. Now the ramp will also push up on the block. Sorry. And this normal reaction will always be perpendicular to the contact. So since the contact is like this, the normal reaction will be perpendicular to it. Now we want to balance the forces. So why don't we write down the components of the force along components of mg along these two directions. Now from geometry, you can check that if this angle here is theta, then this angle over here is theta, just from properties of geometrical properties of triangles. And if you remember, suppose you have some vector v, and this angle over here is theta, then when you try to resolve this vector, the side which is along this angle theta is always v cosine theta, and the component which is on the other side is always v sine theta. So same thing we will do to this mg. The component of mg along this is mg cosine theta, and the component along this axis is mg sine theta. Now we have taken care of all the forces. There is no other force that's acting. Now we are ready to apply Newton's first and second laws. Along the, so we know that this block is only sliding down the ramp. This block isn't jumping, which means that n and mg cosine theta must exactly balance each other out. If n and mg cosine theta, which are opposite to each other, if they were not equal, then you would have some net force, let's say in the upward direction, then you would have a bouncing block. We are not talking about a bouncing block. He's talking about a block which is sliding down the ramp. So n and mg cosine theta cancel each other out. They balance each other. And then the only net force left is along the ramp, downwards along the ramp. So this mg sine theta. So then Newton's second law says that F is mg sine theta, but F is supposed to be mass times acceleration. And so the acceleration of this block as it slides down will be g sine theta. So that tells you what is the acceleration. Then you solve the differential equation. That will tell you what the velocity is. You can find out what the displacement is, etc. Okay. What if there was friction? Now friction has two properties. First of all, friction, the direction of the friction is always opposite to the direction of motion. Because it tries to stop the motion. And the second is that the force of friction is always proportional to the normal reaction. So I'm just going to add on to the same drawing over here. So the force of friction is going to be proportional to the normal reaction, and it is going to be opposite to the direction. Now, since the direction of motion is downwards along the ramp, the force of friction is going to be in this direction. So F fric. And the constant of proportionality over here is denoted by mu s, where mu s is called the coefficient of static friction. Now in our example, we have seen that normal reaction is just mg cosine theta. So I'll plug this in. F fric is mu mg cosine theta. And now in the downward direction, if I want the acceleration, now ma is no longer just mg sine theta. It is mg sine theta minus F fric, because mg sine theta is pulling it down, but friction is trying to prevent it from going down. So this becomes mg sine theta minus mu s mg cosine theta, or A is g sine theta, g times sine theta minus mu s cosine theta. So if mu s is small, if mu s is 0, then it just becomes g sine theta, which is the same thing that we saw before in the absence of friction. But if you increase the amount of friction, so this coefficient mu s becomes large, then you see that the acceleration becomes small. At some point, acceleration will become 0 when sine theta becomes equal to mu s cosine theta, or mu s becomes tangent theta. And this is something that you have probably experienced. If you take a sloping ramp, and so let's say you have this kind of a, if you can see the video, here's a sloping ramp, and if I put something on it, then right now there's a lot of friction, and this is not going to slide down. But as I increase the angle, then eventually it does slide down. So if tangent theta becomes large enough, then you can overcome the friction. Okay. Any questions on this so far? Okay, good. I'm a little confused with the time. 10:35 we started. Okay, we still have some more time. Okay, let's take one example in which we're talking about tension in strings. So I'll take, let's say there is the ceiling, and I'm going to hang a block from, let's say I'm hanging it from 2 hooks. So there is one hook over here, there is one hook over here, and I have some 2 strings. Let's say they make an angle θ1 over here and angle θ2 over here. So I'm hanging this block from here. If you want a biological example, why don't I hang a penguin? So here is your biology example of a penguin hanging from the ceiling. So what are the forces acting on this penguin right now? First of all, there is, let's say the penguin has mass m, so there is gravity acting on it, mg. But now in the strings, there is also a force of tension, which is, and that's always along the string itself. So let's say there is one, in this first string, there is tension T1. In the second string, there is tension T2. So these are the 3 forces acting on it. And what we are going to do is we are going to try and balance out the forces again. So say I'm going to try and balance the forces in the horizontal and the vertical directions. If this angle is θ1, then this color. If this angle is θ1, then this angle is also θ1. And if this angle is θ2, then this angle is also θ2. So this T1, you can resolve it. In this direction, you will get T1 cosine θ1. And in this direction, you will get T1 sine θ1. Similarly, for T2 also you can resolve it. In this direction, you will get T2 cosine θ2, and in the vertical direction, you will get T2 sine θ2. Now it's just a question of equating the horizontal forces and the vertical forces. So in the vertical direction, upward there is T1 sine θ1 plus T2 sine θ2, and in the downward direction there is mg. And in the horizontal direction, to the left is T1 cosine θ1, to the right is T2 cosine θ2. So these are 2 equations in 2 unknown quantities, T1 and T2. Mass of the penguin presumably is known. Since you are the one who has hung the strings up, you can always measure what are these angles θ1 and θ2. So there are only 2 unknowns, T1 and T2, and there are 2 equations. So you can solve these 2 and you will get what are the values of T1 and T2. Here there is no overall acceleration in the end because your penguin is just static. It is stuck over there. Nothing is falling, nothing is moving. So this kind of problem is called a statics problem, where you're balancing out the forces, but there is no overall acceleration in the end. It's just a stationary object. And what we did previously was more of a dynamics or a dynamics problem with kinematics in it, because something is moving. There's a block which is sliding down, there is a ball which is falling to the floor, and so on. Questions? Okay. One last example with Newton's laws. So you've seen sometimes if there is a string somewhere, then you might find a fly kind of hanging from it vertically. So we're going to try and analyze what exactly is happening with that fly. This is again a statics problem. There is no overall motion in the end. It's just a fly or a mosquito or whatever insect hanging upside down from it in a stationary manner. So let me take a cross section of this. So this string is actually like, it's like a rope or something. So it's a cylinder. If I take the cross section, it'll look like a circle. So this is the cross section of the string. And the insect is underneath it. And let's say its legs are kind of like this. So this is horizontal over here. And then it's holding on to this like this. So this is my diagram of an insect, and this is why I am not a biologist. So what we are trying to do is we are trying to analyze how this insect remains stationary with the help of Newton's laws. So what are the forces over here? Once again, this insect has some mass m. So there is a downward force mg. And now you can think of the leg of this insect as having some tension in it. So let's say there is some tension in this leg T. And from symmetry, I can say that each of these legs has the same tension T. So now what are the forces that are acting? Let's call this angle theta. So in the upward direction from here, this is T sine theta. And in the horizontal direction, there is T cosine theta. Same over here on the other leg also, T cosine theta horizontally, T sine theta vertically. So now let's try and balance out the forces. Vertically, I have downwards is mg, and upwards, what is the total upward force? Anyone?
Would
I
it be
need,
2t sine theta?
I need your biological expertise. Is it going to be 2t sine theta? How many legs does a fly have?
6t sine theta.
Excellent. 6t sine theta, because each of those legs is going to do the same thing. And horizontally, well, horizontally nothing happens because all of the left legs are having t cosine theta towards the right. All the right legs are having t cosine theta towards the left. So everything cancels out. So over here you will get 3t cosine theta equals 3t cosine theta. That's just useless for us. Important thing is this equation. So this tells you what is going to be the tension in the leg of the fly. And you can see that it depends on what is the angle. So instead of sitting like this, if the fly was sitting like this, where the angle was more, then sine theta would be more and t would be less. So the angle with which the angle at which the legs are bent and the tension in the leg are correlated with each other. T is inversely proportional to sine theta. Okay, any questions? All right, let's take a 3-minute break.
Can you use correction? तो 90 डिग्री पे जाएगा, साइन would be 160, तो t would be minimum. So it wouldn't.
Sorry?
Oh, I was just. Shit, oh my god. Oh, I was just thinking about how we aren't considering. Just thinking how when sine theta is 1 or theta is 90, at that time the tension would be least, i.e. the fly would have to do least work, but it wouldn't hold itself up because it would just slide off the string.
Why do you think it would slide off the string?
Since all the force is then just in the upward direction, not holding onto the string, right? There's no friction.
So you have caught me out over there. There are some more forces over here, which I did not talk
We are
about.
not accounting for friction is what I was thinking about.
Exactly. So there are two more forces.
Friction are normal.
So over here, there is normal force.
Yeah.
And because normal is over here, and if you think your fly is going to slide downwards, there is also friction in the upward direction. So that also you have to take into account.
Mm-hmm.
Good, very good point. Okay, let's start. So far we have discussed Newton's laws of motion, and So these deal with force. Now we are going to start talking about one more quantity, which is energy. So first we will discuss kinetic energy. This is the energy possessed by a body because of its motion. So motion means this body has some velocity. So this is given by half mv square. Or if you want to write it in terms of momentum, remember that momentum is mv. So then you can write this as half m. V is p divided by m. So this is p squared divided by 2m. These are both equivalent ways of writing kinetic energy. How do you understand this? So if you look at this half mv square formula, suppose you compare two things. You compare a grape and you compare it against a bullet. Both of them have the same mass, but they both have very different velocities. Which is why if someone shoots you with a bullet versus someone throws a grape at you, you know that the bullet is going to hurt you more, because the bullet has a lot more kinetic energy. In spite of both having the same mass, they have different velocities. Or you can think of, let's say, if there is a car which is traveling at, say, 20 kilometers per hour, versus, let's say, there is some bird which is flying at 20 kilometers per hour. So now both have same speed, but if the car hits you versus if the bird flies into you, then the car is going to hurt you a lot more because the car is more heavy. So same V, but different M. So because the kinetic energies are different in the two cases, they carry different amounts of energy in them. And related to the concept of energy is also the concept of work. So work is, you can think of the energy that is needed for a force F to produce a displacement D, and then work is given by F dot D. So this is the vector dot product or scalar product. In other words, you can think of, so if you're applying a certain force, then the work takes care of the force that is done in the direction of the displacement, or displacement that is happening in the direction of the force. What I mean is, suppose there is some block over here and I am pulling this block diagonally. And as a result of it, let's say the block starts to slide along this. So if this angle is theta, then the component of the force along the horizontal is F cosine theta, and the component of the force along the vertical is F sine theta. And because of this force, let's say this block starts to get displaced in this direction. Then the work done in doing this is F dot D, which is F D cosine theta. So it's only the component of the force along the displacement which contributes to the force, contributes to the work. The other perpendicular component of the force, F sine theta, is immaterial. Now, Newton's law says that if you are applying force, then there is going to be an acceleration. Acceleration means velocity is going to change. So you can think of the work as being the difference in the kinetic energy, or K2 minus K1. So half m2 square minus half mv1 square. So to give you a simple example, suppose you take a ball and you throw it up. Now its velocity is changing because of gravity. So initially when you throw it up, it has some speed, but as it goes higher and higher, its speed is decreasing. That means some work is being done somewhere. You can think that the ball is doing some work to overcome the gravity of the earth. So because that work is being done, the kinetic energy is changing. Any questions about work? So here we talked about work in the context of energy, but you can also think of it the other way. You can say energy is the capacity that a body has to do work. The capacity of a body to effect a displacement because of some force. That is energy. And so far we spoke about kinetic energy, but there is also potential energy. So kinetic energy was the energy because of motion, because of velocity. Potential energy is energy because of the position or the configuration of the object. So kinetic energy, as you see, is dependent on the velocity. Potential energy will always usually depend on the location. So there will always be some variable in the potential energy formula which contains the location of this body. So for example, if you're looking at gravitational potential energy, this is given by mgh, where this h, m is the mass of the body, g is acceleration due to gravity, h is the height of the body. So if this is the ground, reference, earth, whatever, and let's say you have 3 balls at 3 different heights, then each of them has different potential energy. This one has mgh1, mgh2, mgh3. Now, when you throw a body up, that is a hand, by the way. Let's say you throw a ball up. At the bottom, let's say over here, potential energy is 0 and kinetic energy is maximum because here is where you threw it. You gave it some velocity. Now, as it goes up, your potential energy increases because you're going higher up, but the kinetic energy decreases because the ball is slowing down. And so potential energy is increasing, kinetic energy is decreasing. Finally, once you reach the top, right at the top, the ball stops. So no velocity, kinetic is 0, and potential energy is at its maximum because it is at the highest possible position. And then it starts to fall down, and the same thing happens in reverse. Now the potential energy is decreasing because the height is decreasing, but it's getting faster and faster, so kinetic energy increases until at the bottom, again, potential energy becomes 0, kinetic energy becomes maximum. But what happens is that the sum total of kinetic energy plus potential energy is always going to be constant. And this is a consequence, this is an example of what we call the law of conservation of energy. This is one of the most profound statements about the universe that we know of in physics, that no matter what happens, total amount of energy always has to be the same. You cannot just randomly produce energy out of nothing or destroy energy out of nowhere. This is not some Harry Potter universe where you can wave a wand and create energy. You can always convert energy from one form to another, but you can never create or destroy energy. So that's the law of conservation of energy. There's one more very useful conservation law, which is the law of conservation of momentum. And I will call this linear momentum, because later we will also see something called angular momentum. So law of conservation of energy always holds. Law of conservation of momentum will hold as long as there is no external force. And this you can kind of see from Newton's law itself, because Newton said that force is rate of change of momentum. But if there is no external force, so F is 0, then momentum has to be constant. So let's look at one example. Suppose this is the Earth and there is some ball which is falling. So if you're looking just at the ball, you will say that, sure, the ball is experiencing an external force, which is gravity. And that is why its momentum is changing. Its momentum is not constant. So if you're just considering this ball, then you cannot apply law of conservation of momentum because there is a force acting on it. But what you can do is you can consider this total system of Earth plus ball. Now gravity becomes an internal force. Externally, there is no force acting on it. So you can say for this combined system of the ball and the Earth, total momentum has to be conserved. What this means is that when the Earth is pulling the ball is also pulling the Earth. A very small amount, of course, but it is. So the ball has a momentum P1 in the downward direction towards the Earth, but the Earth will also have a small momentum P2 in the upward direction towards the ball. And these P1 and P2 have exactly to be equal so that total momentum is conserved. Now you can calculate, you know what the masses are. So M1 V1 is M2 V2. So you know that your ball probably has a mass of, I don't know, 100 grams, 200 grams, and it's falling with some velocity, let's say 5 meters per second. But the Earth has a much larger mass, 10 to the power 24 kilograms. So the velocity of the Earth will be, it'll be hardly anything. It will be something like 10 to the minus 24 meters per second square. So it's tiny. It's not an observable effect, but it is there, and it comes from conservation of momentum. Any questions about this so far? Okay, then since we have introduced conservation of momentum, let's talk about what is called the center of mass. Intuitively, you kind of understand what center of mass means. But in general, the position of the center of mass, which I will call RCM vector, you can think of it being as the average position of a body. So if a body is composed, suppose this is some body, you want to find its center of mass, then we'll break it up into lots of small pieces. In general, suppose this is some piece over here which has mass mi, and it is located at this location ri. Then the position of the center of mass of this body is given by summation mi ri divided by summation mi. So you can think of this as some average position of the body. And all of these Newton's laws that we've been looking at, all of these forces that are acting, you can think of the force in, so of course it's an extended body which has lots of parts, but from the point of view of applying Newton's laws of motion, you can think of this entire mass of the body being concentrated at the center of mass itself. And then you can apply Newton's laws to that center of mass. So that's what allows us to analyze various complicated motions using just simple Newton's laws, in spite of the fact that the body itself can be quite large and quite complicated looking. So I want to share, one second, do I have it over here? Probably not. So I want to show you a picture, a couple of pictures actually, and this is in the Resnick and Halliday book, so you have access to it, but I just wanted to bring it to your attention anyway. So let's stop sharing on this and let's start sharing over here. So can you see? So if you did your reading last time, and if you have read about projectile motion, you will have seen that when you throw something in the air, it makes a parabolic path. And of course, over there, ideally, we just considered like a point body or a small thing like a ball. And you analyzed its motion and you found that it has a parabolic path. But the point is, suppose you also, even for some large complicated object like over here, this is a baseball bat, you can see that even though the whole bat itself has some complicated motion, if you just look at its center of mass, the center of mass is following the same parabolic path that you studied in projectile motion. So as far as just the center of mass is concerned, you are perfectly fine applying your very simple laws of motion over there. There is one more picture in this book somewhere which shows a dancer. Here it is. So here again you have a dancer whose motion in general is quite complicated. But if you just look at the center of mass of the dancer, you can see that it follows a parabolic path or a very simple curve which you can predict using laws of motion as applied only to that one single point. I also have a couple of things over here which I wanted to share. So the quality of the picture is a little bad, but here's a fish that is jumping out of the water. And you can see that again, while the fish itself is quite complicated and it does its own thing, overall, the motion of the fish is again given by a parabola, which is what your projectile motion equations would predict. Or here's a person jumping off a pier and into the water. Again, projectile motion. Even though the person does strange things with their hands and legs and moves around, the center of mass of the person will still continue to follow the same simple path. So that's why the concept of center of mass is very useful when we are doing physics. It allows us to take complicated bodies and explain their motion using very simple equations of motion. There's one more reason why center of mass becomes important, and that is to do with issues of stability. So suppose I have some object that looks like this. You can, and let's say I put it on the ground. Now you can imagine that the center of mass of this object is probably somewhere over here. And this is, the center of mass is within the base area of this object, which is why you can think of this object as being stable. But the same object, now if I try to put it like this, no. And now the center of mass is over here, but the contact of the base of this is just this much, and the center of mass is kind of outside that. Then for this, you will say this is unstable. Or if you have the human body, then the center of mass is somewhere in the abdomen, and that's fine. But now, if this is a human who is carrying a very heavy bag, then the center of mass is going to shift outside towards the bag, which is why to make yourself stable, then you will probably lean towards the other side. So that the center of mass again comes inside you. You can't really see this person leaning, but I'm hoping you get what I'm trying to say. Something like that. You will try and lean towards the left in order to, if you have a heavy bag in your right hand. So that is to ensure your stability if your center of mass changes. Or for example, a drunk person who is tottering around, and finally they might tilt to such a level that the center of mass is now outside, and then they're going to fall on the ground. Okay, so that was to do with the concept of center of mass. Now, how much time? 15 minutes. Okay, we can start discussing the concept of rotation or rotational motion. If you know linear motion in physics, rotational motion is almost exactly the same. So I'll just draw a table over here. Linear motion rotational motion. Achha, what do we mean by rotational motion? So we are thinking about, let's say, some object which is moving in a circle. So let's say this is a circle of radius r, and it's moving. So its movement along the circle is given by the angle theta. Normally, if you're doing linear motion, then the motion is given by the actual displacement x. But in this case, the corresponding variable to define the motion is theta. Now, if you want to define the velocity over here, you will take time derivative. Same thing over here, if you want to define angular, so this is linear displacement, this is angular displacement. Linear velocity, angular velocity. Same, take derivative with respect to time. By the way, what is the relation between x and theta? So if this was linear motion, so if this was x, then you would say x is r theta from geometry. And then when you take derivative of this, so that gives you v equals r omega. If I want to find linear acceleration, then this is dv by dt. Similarly, if I want to find angular acceleration, this is d omega by dt. And once again, dv by dt is r d omega by dt. Therefore, a is r alpha. Then we derived some kinematical equations. So we said v is v0 plus at. We had x is v0t plus half at square. We had v square is v0 square plus 2ax. These were the three kinematical equations that we defined last time. We derived them actually. Exact same thing is going to happen with the angular variables. So final angular velocity is initial angular velocity plus angular acceleration times t. Theta is omega 0 t plus half alpha t square. Omega square is omega 0 square plus twice alpha theta. So if you're given a problem in rotational motion, just think of how you would try and solve that problem in linear motion, and use the same corresponding equations just with the rotational variables. Now omega is d theta by dt. I can think of this as a differential equation, and I can do separation of variables, and then I can integrate this. And if I integrate this over one entire circular motion, then the time that it takes to complete one entire rotation is called t, period of rotation. And this is the integral over the angle over entire circle, so that is 2 pi. So what this tells you is that t is 2 pi by omega. So if you know what is the angular velocity omega, you can find out what is the time period from there. Or the other way, if you know the time period, you can find out what is the angular velocity. Do I want to start discussing this? Might as well. I have 15 minutes because we start 5 minutes later. Okay, yes, then I definitely want to start. Okay, so we are now going to discuss what is called moment of inertia. So this moment of inertia is given by I, and this is, so once again, if I have some object and if I divide it into lots of small pieces, each having mass mi, and now we define moment of inertia in the context of a rotation. So this is some object, and let's say I have some axis, and I'm considering the rotation of this object about this axis of rotation. Then suppose here is one piece with mass mi and which is at a distance ri from this axis of rotation. Then the moment of inertia is given by the sum over mi ri square. Or if you want to think of this as a continuous body, then you can think of this as integral dm r square, where dm is the mass located at distance r. So for example, just to give you some simple cases, suppose here is my axis of rotation, and I'm just talking about some small particle m, which is going around this axis in circular motion. So then there is no sum because there is only one object m, and let's say the radius of this circle is r. Then for this motion, the moment of inertia is just mr square. Suppose I had an axis and my system was composed of two objects, each of mass m, but orbiting this axis with at the same distance r. So think of this as okay, this is a weird example. Think of this as a bone which for some reason is rotating about its center, and I'm ignoring the mass of the long part. I'm just saying that the mass is at the two ends. Then I is just going to be mr square plus mr square, which is 2mr square. What moment of inertia actually means is how the mass is distributed relative to the axis. So if here is my axis, and suppose I have one object where the mass is right, so this is of course rotating about this axis. Let's say this is a sphere of mass m, and all of this mass is right here. It's quite close to the axis, versus let's say another situation where again same mass, but the mass is kind of distributed like this. So again total mass m, but there's very little close to the axis and there's a lot of it far away from the axis. So then if this is I1 and this is I2, then I2 will be greater than I1. So moment of inertia is measuring how is the distribution of mass with respect to the axis of rotation. Right now, moment of inertia probably seems a little non-intuitive. It seems a little arbitrary. Why the hell did we define something like this? But in the next lecture, I think it will become clear what the role of moment of inertia is. In fact, as we will see, the same role that mass plays in linear motion, moment of inertia plays that same role in rotational motion. So we can try and do a quick calculation of the moment of inertia of some simple object. So we'll consider a rod rotating about its center. So here is a rod. Let's say it's a rod of length L, and it is rotating about its center like this. So let's call this position 0. So this is from minus L by 2 to plus L by 2. So total length is L. How should we find its moment of inertia? Moment of inertia is given by an integral over dm r square. Let's take some small piece of the rod over here. I'm assuming that the rod has uniform density. So if I treat the rod as just being some one-dimensional object with uniform linear mass density lambda, let's say, then the dm over here, the small mass of this piece, is just going to be lambda dx. So let's call this dx at a distance x from the axis of rotation. And r square, which is the distance from the axis of rotation, is just x square. So this is going to be lambda integral x square dx from minus L over 2 to L over 2, because I'm integrating over the entire rod. And this will give me x cube over 3, L cube over 8 twice. But lambda times L, mass density lambda means lambda times L is the total mass of the rod. So 412 ml square by 12. But now the same rod, instead of rotating it about its center, if I rotate it about one end, the same rod, but now not rotating from the center, but rotating around one end of it. Once again, same way we'll do it. So now this is from 0 to L. So integral dm r square. So at some distance x from here, let's take a small piece called dx. Once again, the mass of the little piece is lambda dx. Distance from the axis of rotation is x square. But now this integral is not from minus L by 2 to L by 2, it is from 0 to L. So this is lambda by 3 L cube. And this becomes ml square by 3. So you can see that the object is the same, the mass is the same, but because the rod on the right hand side is rotating about its end, means the mass is distributed farther away from the axis of rotation. Its moment of inertia is more compared to this case, where the mass is more closer to the axis of rotation. And then using moment of inertia, one can define rotational kinetic energy as half I omega square. Now you can see why I was saying that moment of inertia plays the same role as mass, because in linear motion, you have kinetic energy is half mv square. So linear velocity, angular velocity, okay. But mass is like moment of inertia. So it plays the same role as mass does in linear motion. Any questions so far? Okay, if not, then we'll stop here for today. And in the next lecture on Wednesday, we'll continue a little bit of the discussion about rotation, like in terms of the physics theory. And then after that, we will look at some biological examples, and which will make these concepts a little clearer for us. So it's going to be a lot of work for me. Okay. And by the way, tomorrow we have office hours. So if you want to come and ask some questions, feel free to do that. Okay. Thank you.